What's it getting at? Okay. First question is a very leading question that you'll find in most papers to just get you going. Very straightforward question. That's looking at energy stores. But it's important to get the terminology right. We're looking at energy stores. And this particular here, it's asking you very specifically, which of these particular objects would have elastic potential energy in its store? Now, elastic potential energy is about things that can be compressed or stretched. There are only two of those particular objects on there that would store any kind of potential energy in a compression or in terms of stretching. And it will be obvious to be the bungee cords, where you stretch, usually over something to keep something in place, or indeed the fairground ride there, which is on two springs or shock absorbers. As one is being compressed to dip down the front, the other one is releasing energy from the spring at the back and backwards and forwards, so it rocks backwards and forwards. If you're not writing this down, I suggest you do write this down, Lewis. Good lad. So, why though? Why? Explain why. That's 2 marks out of a 3-mark question. Why? Because actually, with elastic potential energy, they will return back to their original shape. Once all the energy is being transferred, they will transfer back to their original shape. And again, the next question is looking at a required practical that we do. You may have done, probably have done by now, which looks at extension when applying a load or a weight to a spring. And if any of you can remember what the law is in terms of extension, if you can't, then you should be able to remember it. Hooke's law. Now I've put the graph next to. I'll put the spring in terms of the extension next to the graph. We all got that? So you've got the graph and the spring. Which one of the following is the unit of weight? Which one of the following is the unit of weight? Weight is not mass. Weight is not measured in kilograms. Weight is a force. So therefore, weight is always measured in newtons. The weight of something is a function of the mass of that object multiplied by the gravitational field strength in which that object is. So on Earth, the gravitational field strength of Earth is about 9.8 newtons per kilogram, sometimes rounded up to 10. If you're asked to use the gravitational field strength, and you will be, it will be given to you. Don't assume it's 10. It'll either be given to you as 10 or as 9.8. But weight is not the mass of something. Mass is measured in kilograms. Weight is a force measured in newtons. So what range of weights did the student use? You need to go back and have a look at the actual graph, and the answer is clear. 0 to 5 newtons. You would have been given a mark for saying 1 to 5, because there is an argument to say that 0, there's nothing there, 0 isn't part of the range. But the graph says 0 to 5, because the graph is drawn from 0 to 5. So 1 to 5 would be acceptable, and you would have got the mark for that. But 0 to 5 would also be the correct answer. So 0 to 5 newtons. How far does the pointer move when 4 units of weight are on the spring? Well, just simply look at the spring. 16 centimetres. Read off from the spring, or indeed from the graph, 16 centimetres. Without much scientific background, without much scientific knowledge here, you could pick up marks. So the student ties a stone to the spring, and the spring stretches 10 centimetres. What is the weight of the stone? Well, very straightforward. Use the graph, 2.5 newtons. Okay, read across from 10 centimetres, read down, 2.5 newtons. Anywhere from 2.4 to 2.6, depending on where you draw that line from 10 centimetres.